All right, so in this video, we're going to be looking at how to enter some data into R, and then we're also going to be looking at manipulating that data and then calculating some basic descriptive statistics on some data, and then also from sample data frames that are already incorporated in R. Now, to enter data into R in the simplest possible way is simply to enter the data as a list, which has this syntax C and then parentheses, and then you list the values and you close your parentheses. So this enters the data as a list or a vector, and you simply save it as X1 or X2 in this case. So depending on how long your data is, if you're just doing a very simple example, you might have the data printed out on a piece of paper and then you need to enter it into R somehow. If you have data to enter from, let's say, an Excel file or something like that, then there are import functions that you can use that I've described in other videos that you can import data from Excel or other file formats into R. But in this case, very simple, we can just list out the values. Now, I can perform operations on these values much the same way that I would simply adding columns in Excel. For instance, I can add corresponding values of my data together. So for instance, here I'm adding the values in X1 and X2 together, and this will add corresponding values. So I can see down here, if I print it to the screen, I've added 2 and 3 is 5, and 5 and 6 is 11, and so forth. So I can combine data once I've entered it into R just by doing operations on the vectors. Similarly, you can do this if you have a data frame. You can add columns together in much the same way. Now, if I want to calculate some descriptive statistics, I'm going to start with a list of values. In this case, this is the number of moons for each of the planets in the solar system, including Pluto. The current list of statistics has Mercury with 0, Venus with 0 moons, Earth with 1, Mars with 2, Jupiter with 95, Saturn with 146, Uranus with 28, Neptune with 16, and poor little Pluto out there with 5. Now, if I want to calculate first I'm going to enter this into the memory, and then if I want to calculate the mean or the average, I just use mean of X, and it will output down here. I can do standard deviation of X. Now, the thing about the standard deviation is that it is always the sample standard deviation in R. If I want to calculate the population standard deviation, I have a couple of different options. So for instance, I can create a function that will use the actual formula for the standard deviation, or I can actually multiply it by, in this case, multiply the essentially the variance by the length minus 1, so that take out the denominator, and then divide again by the actual n instead of the length, instead of n minus 1. So remember, that's the main difference between the standard deviation for the statistics and for the sample versus the population. The sample you divide by n minus 1, and in the population you just divide by n. So here we're essentially taking out the n minus 1 and putting back the n. So we're going to use the length function to calculate the number of values. And so in this case, I'm creating a function, sd.p, and then I can use that function to calculate the population standard deviation, or I can simply, in this case, calculate the sample size, and then just directly on the screen, take that standard deviation and then multiply it by the square root of n minus 1, and then divide it by the square root of n. So it's just that scaling factor that needs to be adjusted so that you're dividing by n instead of n minus 1. Now, if I want the number of observations, again, that's just the length. I can calculate the minimum and the maximum values by just using these min and max functions. If I use the quantile function, I can use this to calculate a specific quantile, let's say just the 25th percentile, or I can use it to calculate a string of quantiles. In this case, the 25th percentile is the first quartile, the 50th is the median, and the second quartile, and then the 75% is the third quartile. And if I run this, it will just give me all of these values, but it displays them, the quantiles, as percentages. Remember, these are observation values. I can calculate the median without using the quantile by just using the median function. And we can see that the 50th percentile and the median agree with each other. I can calculate the IQR directly instead of calculating Q1 and Q3 and subtracting. And if I run that, I get 27. And again, notice that is Q3 minus Q1 gives me 27. And then I can also calculate the variance, which again this is the, if I think back to my examples, this is the population. This is the sample standard deviation, sample variance, not the population variance. So kind of keep that in mind as you're doing these examples, because if you're calculating the sample variance, then you're going to need to do, then you can just use the var function. But if you're calculating the population variance, you're going to need to use a trick similar to what we did up here, just without the square root. So you would calculate the variance times n minus 1 divided by n to get the population variance. Now, we can also get other statistics. Different packages have different kinds of functions in them that we can employ. So for instance, this package moments, and again, install it under tools if you've never used this package before, has functions for skewness and kurtosis. Now, these are less common statistics to encounter, but they have to do with how spread out the data is in terms of how essentially how normally distributed it appears. And of course, just the skewness. Is it more to the left or more to the right? So we can calculate these values. If it's 1, or if it's 0, I believe it's normally distributed, essentially centrally distributed. And if it's positive, it has a positive skew, so to the right. And if it's negative, it has a negative skew to the left. And again, kurtosis, again, it's a way of comparing your distribution to the normal distribution. Now, one thing to kind of keep in mind is that kurtosis is sometimes compared to, is sometimes calculated in slightly different ways. Sometimes it will be calculated according to this moment formula, and then people will subtract 3 because the normal distribution comes out as a 3. And so you want to make sure that you know how the package is calculating your kurtosis, because this value might mean slightly different things depending on how they calculate it, whether they've subtracted that 3 or not. Now, one of the other measures of central tendency that we often talk about in descriptive statistics is the mode. And the problem with the mode is that if you're calculating it on numeric values, it just gives you numeric. Even when there is an actual mode in our data, which is 0, but it just doesn't like to cooperate on numeric values. Now, if I want to, I can create a list of descriptive statistics that I want to calculate all of the time, and I can create myself a little function. Now, there are packages in R that I've talked about in other videos where they have functions that will do descriptive statistics, sort of all collectively, a preset set of descriptive statistics. And different packages will provide you with different sets of statistics. But you can create your own function that will give exactly the specific descriptive statistics that you want for whatever your application is. So in this case, I'm creating a function. I'm going to import the library moments inside of this function to make sure that it's available, and I've created a list of the statistics that I'm going to calculate. Mean, sample size, standard deviation, population sample deviation, sample variance, the minimum, Q1, the median, Q3, the maximum, IQR, range, skew, and kurtosis. So those are the list of things that I'm going to calculate. And then in my values, I'm actually doing the formulas. So mean X, length X, so on and so forth. I'm not using my prior function that I calculated before. That's fine. I'm just doing the standard deviation times n minus 1 over n, calculating the variance, the min, quantile is 0.25, quantile 0.75, again, IQR. The range is the max minus the min, skewness, and kurtosis. And then what I'm going to do is I'm going to combine these two using rbind in this case, which will take my two vectors that are in rows and attach them on top of each other so that the labels become the labels for the data in the second row. And I'm going to combine the stat and the value. Now, if you want them in columns, you can also do that. If you use cbind, then they'll be attached in columns, and you'll have the first column will be the labels, the stats, and the second column will be the values of those statistics. But I'm just doing rbind just to help organize it so that everything gets displayed nicely. And then I'm going to return that table of 1var stats. So if I go ahead and I run this function, then I can specify just in here what data set that I want to perform those statistics on. So if I do it on my moon data, then I get this table where they're listing out the individual values. I could, if I wanted to, I could also apply a rounding function, for instance, in order to make some of these values display a few less decimal places if I wanted, but this is fine for this example. I can also, if I pull in a data frame, for instance, MT cars, which is one of those data sets built into R, I can choose to calculate my 1var stats on, let's say, one of the columns. And again, these are my statistics from that MPG column in 1var stats. Now, there is one other thing that I can do in terms of somewhat common statistics is that I can calculate a trimmed mean. So in this case, the trimmed mean, what it does is it takes a certain number or a certain percentage of values off of either end, and then it recalculates the mean. So if you have very skewed data, you can take out the outliers symmetrically on both sides, and then you can recalculate the mean from there. It's sort of a compromise between a mean and a median. So you'll get a little bit closer to the median because the outliers, if there are any, won't affect the value as much. But it won't throw away all of the values. And so you may still get some information about a skew, depending on what percentage that you take off. Now, it's worth noting that the trim percentage here at 10% takes 10% off of each end. So it's actually taking 20% of the data away. So it's just something to kind of keep in mind. And if we run this, I got an error when I tried to do this on my, I got a warning message when I tried to do this on my planet data, but it did work without an error on my MPG data. Probably the size of the data set has something to do with that. But when you do a 10% trimmed mean, you get this. And we compare that to the value of the mean in the original, we have 20.09. So again, there's maybe a slight right skew. You can see the skew here is positive, but not very large. And when you calculate the trimmed mean, it'll slide a little bit closer to the value of the median, which was 19.2. So the mean is a little bit above the median. When you calculate the trimmed mean, you get it a little bit closer to the median, but not necessarily all the way. It's still being affected by that positive skew.